Okay, let's get started. Are you able to hear me, right? Because it's very silent. Yeah. Okay,
I
cool.
can hear you.
Nice. So, yeah, welcome to our second session. I will cover in a few minutes what we're going to cover today, what we covered in the last session. I will just introduce women coding community for those who joined us first time. Even though I see a lot of people joining, and thank you so much, not the first time. Um, 1 second, I'm sharing my screen. Yeah, so a few minutes about women coding community, and then we will start our session. So, women coding community, it's building a safe environment for women to thrive in tech. It was launched 1 year ago, a little bit more than 1 year ago. So it's than 2,000 women we have in our community nowadays. So our mission is empowering women to be at the forefront of technologies and innovations. Women coding community vision, empowering women in their tech career through education, mentorship, community building, and career services. We provide workshops and events, connect members with industry mentors, foster a supportive community through meetups and conference, and raise awareness for more inclusive industry practice. Code of conduct. At Women Coding Community, we are committed to a vibrant, supportive community where women can network, share experience, and foster professional relationship, regardless of age, gender, visible or invisible disability, ethnicity, gender expression, level of experience, education, social economic status, nationality, personal appearance, race, religious, sexual orientation, or prefer programming languages. Our projects we have many projects. The main idea that we have mentor programs, which is long term and ad hoc. A part of mentor program, we have different study groups. We have so this is one example. This is system design study group. We currently running lead code bootcamp, which takes 12 weeks. We already cover 3 weeks. More ahead. So a part of it, we have LLM study group, which is also not only study group, but they having a similar bootcamp like we have for lead code. It's also 12 weeks. And I believe they started similar like lead code maybe 3 weeks ago. A part of it, we have different studies groups. We are supporting different events. We are having different meetups. So our projects, which is I told. Volunteers. So who wants to start to be mentor or just volunteers? Currently, we are the one thing which is personally me started. We want to find someone who is very strong in marketing or in promotion, because our community is quite big nowadays, and we are missing this part. To create more posts, to upload it quickly our YouTube videos and so on. So if someone wants to volunteer and help community, so just welcome. You can reach me or someone of our leaders. I believe it's a great opportunity just to build some kind of small marketing department in our community. So this the things. Benefits. We have friendly crowd, excellent network opportunities, learning or mastering leadership skills, a nice perk on your CV and recognitions. Sometimes there is we are sharing the, free tickets for different conference. Yeah, that's it. Thank you so much. Now moving to our system design meetup. So basically, if any questions from the last week, feel free to ask, like 5 minutes, probably we can spend. Also, I'm going to cover what we covered last week. Do you have any questions? Okay, cool. If no questions, then I'm moving to so what we have covered, just like a reminder, and also for those who didn't join us last week. So we started from system design requirements, and I try to understand how the thinking process during the interview should work. So we basically cover what is the functional requirements. That functional requirements when you define your functional requirements, so basically they just will be mapped after all on the IP calls. That's how functional requirements works. So regarding the non-functional requirements, we started to cover some important terminologies. Last week it was availability. Under availability, we cover fault tolerant, we cover reliability, and we cover resilience. This terminology is very important. Last time I explained it. So when we are speaking about availability, and if during the interviewer saying that I want fast. So, for example, as in this example somewhere, we cover, I want a scalable system. I want my availability being with this 19th range, or I want that latency in my system will be this. So basically, you start clicking and applying some system design concepts. And what we did last week, we started from the terminologies, what the scalability, what availability is exactly means, and what kind of system design concepts we should learn in order to meet this non-functional requirement like availability. In this session, this is second part. We are going to cover terminologies slash non-functional requirements like durability, scalability, consistency, and performance. So this is the most popular non-functional requirements, which is you most likely will be covered during the system design interview. A part of it, there is three will be left, which is maintain, cost, and security. So I will probably just create some post on the Slack where I will cover maintain, cost, and security requirements, because it's very rarely where you will cover them. Okay. Any questions? Or I can start. Okay. Let's start from the scalability requirements. So the scalability, it is the property of the system to handle a growing load. What load could be? It could be request per second. It could be volume of incoming or outgoing data. It could be number of concurrent connections. Most of you, I believe, know what does mean scalability. We can scale our system vertically, or we can scale our system horizontally. It's also calling like scaling up and scaling out. What does it mean? The circle, it means clients, and here servers. So when we're speaking about vertical scaling, we means that we will scale our server. So we will scale hardware. So for example, assume you have machine with 16 CPU, and you will scale it to 64 CPUs, for example. So we are scaling basically hardware. We are not adding any new machines. When we're speaking about horizontal scaling, it means that we are adding more machines. It could be less powerful machines, but you're increasing the quantity of the machines. During the interview, there is no like white or black. What is better, what is not. So with your seniority, you will show with the most you senior will be senior engineers. You will know that there is usually hybrid approach, because you should understand when it comes to the vertical scaling, there is certain limits after which even very powerful machine won't scale enough to serve your traffic or ongoing data or number of concurrent requests. So there is limits on the vertical scaling, and usually the more powerful machines, the more cost of this machine. On the other hand, horizontal scaling comes with the complexity. It always comes with complexity. I will explain what I mean with challenges or complexity. Once you go with horizontal scaling, you certainly will need to add additional components like service discovery, load balancing, request routing problem you will need to solve. Also maintenance. So to maintain one machine, it's one thing. To maintain different service, it's another one. Machines, it's another one problem. Um, So on this end, do you have any questions? Or Shailaja, if you want to add something.
No, I don't have.
Okay. Yeah. Okay. When it comes, the one things which is I want to add this nuance while I was preparing this. It's usually when it comes to replication and scalability, there is small confusions which is I want to cover. You could add replication, which is will cover the availability aspect. But if you're adding your replication in active passive pair, means you're adding, for example, you have one leader node and there is a standby replication, which is just standbying, but they do not serve the actual traffic. It could serve read. So in this case, it's not actual horizontal scaling. It's we are covering the availability or durability, or resolving fault tolerance requirement on this end. So also with scalability usually comes another one terminology, which is elasticity. There is, it's slightly, I want to cover what is difference between elasticity and scalability. Scalability, which is we cover, we provision resources. Resources here is our service machine nodes. We adding incremental, in incremental manner over the time. Depends on how our traffic is growing, how the system become popular. So you're adding these nodes with the time incrementally. But there is existing another terminologies, which is elasticity. It means that you grow or shrink your infrastructure resource over short time period. So, for example, you know that in some region or during some global event, you would need 10 machines. And before this event, you will actually deploy this 10 machine. You will add this redundancy of 10 machines in order to serve this spike of traffic during some short period of time. This is we calling elasticity instead of scalability. It's usually done in order to save cost, because to save cost on the servers, and also to reduce cost of maintainability.
Livia, I have one quick question. Does do we do we implement elasticity in database side? Because it, I don't think we really do elasticity in database side, right? Because we need persistent database, isn't it?
Let me answer from the cloud infra, and Shailaja will answer you from the database, because she's working on Cassandra. So basically, when you're using DynamoDB or you're using S3, it comes out of box. Usually, you can configure that your DynamoDB nodes actually scale during the some traffic or during some events. You can add this elasticity.
Okay, let me explain a bit, because this is a new word we have introduced. So
Mhm.
usually just per the system design interview perspective, you don't need to worry about the elasticity because usually you don't need to cover this part. Usually scalability is the only part which is important. But in the real systems, what we do, the typical, even the database, these are distributed systems. These are running across various machines, not on a single machine. So at times we do have a forecasting, or we probably assume that we will need more machines to be added to this cluster, and we add them. Probably we use them to part of that, and later on we realize some part of the cluster is not being used. So uh, and those are unnecessarily adding the cost to the overall cluster operations, right? So that's why we want to cut the cost, and we try to move a partial data to other system and remove those machines and reuse those machines for some other purpose. So that's where we do the elasticity. That means elasticity is not only increasing the scale, but also the scale means, sorry, they're not only increasing the number of machines to support the scale, also decreasing the number of machines needed so that we can reduce the cost. Scalability, whereas is a user supported for the users operations and requests. So scalability can be the same. For example, you are supporting 100 requests per second. No matter you are using 10 machines or 100 machines behind, probably the scalability scale is the same if the entire system is supporting well with the 10 machines. But if you realize that those 90 machines are sitting idle, you can just cost cut them. So elasticity from the system interview perspective, you don't need to worry. When you're really working on a real system, it's a good to know concept.
Yes.
Yeah, but so like when we were explaining elasticity, we were saying that it's either you scale out or in for a short period of time, right, based on the needs. So
Yes.
my curiosity was about whether databases actually implement elasticity, because how do you scale out and store data? Then how do you shrink back, and don't you lose the data because it looks like it's very dynamic in nature, elasticity?
So usually we do have a automatic workflows written. Even for scaling out as well, we do have automatic workflows written based on the what is the current scale we are supporting, amount of the data, number of requests. The software can automatically make some forecasting calculations and assume that we probably need few more machines by next 3 months. Then it will go and usually we keep some machines in the spares pool which are unused, which can be grabbed by any cluster which is needing them. So the workflows will go and grab them and attach them to the cluster. This is in the software, not really physical. Physically, they are all already connected. In the same way, when we think there are some of the machines which are sitting idle, or the storage is unnecessarily sitting idle, if it is because the when we need to move the data, we may need to move the data, part of the data, not really major, because we are already assuming that some of the machines are sitting idle. And when we are moving the data, these workflows are ensuring that the shrink operation on the cluster is triggered. The shrink operation will move the data, will do sanitization checks, that is this data already existing in the new the machines where we move them to, and only after verifying that they will set those machines free. Those machines, once set them free, those go back to the spare pool. So this all the workflows, even for the scalability, to be honest, we don't go and attach machines manually there. This is all automated. We go and grab new machines from the spare pool, attach them to cluster, and say that okay, we're scaling out. And similarly, elasticity also works. So the workflows are really good enough to verify that the data is moved and perfectly 100% complete. Verification is already done.
Okay, yeah, thank you.
Thank you. Moving on. Next, our non-functional requirements will be performance. So when we speak about performance, we can speak about time required to process something, or a rate at which something is processed. How it maps to the real world. So basically, when the client is requesting some video view from the cloud for example, from some server. We want to download, or we want to watch this video online immediately, almost immediately, with very low latency. So this is time required to process something we are calling. In this case, it will be view video. On the other hand, when you like some video on the same YouTube, on the YouTube or somewhere on Netflix, in this case, it is matter how many reactions the system can handle in a given time. Means it's not like how quickly, because it's instant, right, when you're clicking. But the idea is how many requests you can process and actually visualize this, how many likes you have at in a given time period. So how it is, this is the real world examples, and it is map in time, time required to process something. It is actually latency. I will cover a little bit. So for now it's latency, and when we're speaking rate at which something is processed, we are calling it throughput. Now let's dive deep. So basically, when someone sending request and waiting response, and we're calling it latency, but it's actually our response time. Our response time, it is network delay plus processing time and plus queuing. So basically, network delay, it's include time request spent on the wire, means it is traveling over the internet to the server and on the back. Processing time, it's time which is actually consumed to process your resource on the server. And queuing, you can actually emit, because it's quite emit during the system design, but it's nice to know. Queuing, it means that you are waiting in the queue, for example, in the socket, while server will be able to process your request. So all of these three things combine into response time. Yeah, so and during interview, when you're speaking, this is clear about the response time. Okay, cool. So
One small suggestion during the system design interview, don't worry too much about the network latency, etc., because those are all too difficult to calculate, takes a lot of time, and also most of the time is the network latency is going to be very similar, unless the only time when you are need to worry when you're comparing having a system local and versus non-local across the geography, that's when you probably need to worry about network latency. But otherwise, don't worry too much about making calculations using the network latency. That's going to unnecessarily complicate things for you.
yeah,
Can you just quickly explain queuing again? Because where does queuing happen?
when you're sending your request, you establish connection with your server, and there is a server which is able to at the same period of time able just to process some certain amount of request. But while the server is processing this amount of request, I mean, you already landed, your request was already landed on the machine, on the one machine server. And your server has your service, which is actually doing some processing of your request. And the rest requests are waiting, because there is limited request which is at the same period of time your service can process. All the others will be waiting on the socket, while your machine will be process all the requests and will send it back to the client. Does it make sense?
Yeah, thank you.
Actually, queuing can be at multiple layers, all the way when the request coming to the load balancer. Load balancer may not immediately schedule your request because there may be many requests based on the priority and the importance of the request. They can be in different queue sitting. Once the load balance picks the request and sends to the service to handle it, because nowadays we are having microservices, there are multiple services running, each one of them doing different job. One service might be doing a particular job and keeping it in a queue, something like Kafka, and another service probably taking that request to do some job. So the queues can be involved in various places in an entire system design. So when you are the queuing latency is when you need to consider when you're designing a system and you're telling them that from this service to this service, the request is going, and I'm using Kafka to do this. That's when you need to think the latency that queuing may add.
So are you saying that if I introduce, let's say, a load balancer between a client and a server that is just responding by fetching data, let's say from database, so there are probably three layers of queuing here, one before the load balancer, one before the servers that are serving the request, and maybe also one before the database that's
Yes.
fetching the data, isn't it?
Yes.
Y-
It's,
Yeah, so that varies from the design to design. Some systems probably having more queues, some of them might be having lesser queues. So nowadays, what is happening? The requests we are trying to do, request response is usually asynchronous, because when you're sending request to a system, that system probably doing so many actions and there may be queues involved in multiple places, and the client can't keep waiting for the response all the time. So we usually send the response asynchronously, let the client go ahead and do some other job, and once a response is available, client takes that response and shows to the user. So for all this, we will be some places we will be using web sockets, etc., for the direct connection to the client sending the request. So this will be a recent concept we have got, so we need to cover this later on.
Okay. I think there is also a callback mechanism where the server will respond when it's ready, isn't it?
Yeah.
Thank you.
yeah. So important to understand what we want to improve during the interview. Yeah. So basically, if it's network latency, we should think about. Yeah, Ishalaja told it's nice to understand these OC models and different network protocols. This is 100% which is you will need. For example, it depends on which system design you work. For WhatsApp, you will choosing different protocols. For URL shortener, you will choose another network protocol. So it's good to understand this difference, and we will cover this network aspect later. If it's server-side latency, so what it's also very low-level discussion during interview. But again, because there is different levels, people who is interviewing for different level, but then senior you will go, then more low-level questions you will need to answer. But I agree on the general system design interview for the middle position, and probably not like fun company, probably you don't need to know all these like low level details. For example, like how you can reduce the service side latency, because here on this you will speaking about different algorithms, but you should know that memory is faster that we covered last time, whereas these trade-offs. There is some thread pools, parallel processing, local cache, concurrent connections. So this is kind of things probably it's good to know, and those kind of things will reduce the server-side latency. If it's come to client-side latency, yes, we should talk about blocking
One,
versus.
one
Mhm.
one small correction. It's not, we should know. It's not a good to know or optional. You should know. But you don't spend time on discussing them unless interviewer asks you to explain, because these way are very low level and takes lot of time to discuss, and you probably taking important time of your system design instead of on going depth on this instead of going at the breadth. But it should always good to know, because not only because to explain to the interviewer when he asks, knowing these details well will help you to design a very good design. Also at the work as well, it will help you to uh, uh, infer what's going underlying problems and then fix them properly. So we should know, but just that don't spend much time discussing them unless asked.
Yes, this yeah, this is true. So let's talk about latency, how we actually measure latency. On this example, I try to draw some diagrams, and here we have latency response time, and here we have request. I sorted them. Usually, this request. So, for example, we're taking period of time 1 minute, and during these minutes, could be different latency from the same request, which is you probably will think like they should take approximately the same time. We're sending the same request, and it should take the same approximately time, but it is not true. During this 1 minute time, there is a request which can take a different time. And how we're usually measuring our latency? We're measuring them in percentile. It could be P15, it could be P19, it could be more. So on this diagram, I brought just 2 examples. And usually at the workplace, it's not related much to the system design now interview. It's just what we're doing in the workplace. We measure latency, and usually software developers is trying to solve the problem for P19 and above, even though how to read them. So if we're speaking P99 of 3 seconds means 1% of the request took 3 seconds or more. You will think like you are serving almost 100% of the traffic with acceptable latency, but there is 1% request which is took more than 3 seconds. So usually we're trying to solve this issue and decrease this latency. But again, there is also should be usually taking trade-off because some of the problem to solve and to decrease latency for 1% or less, I would say less, it's very expensive. But yeah,
can you help understand how to read that graph? Because so where you mark, for example, P90 or P50, right? So what does that mean?
So you have requests, and there is like 50% of your request is actually served with 20 milliseconds. Means all requests which is above of this line are served more than with 20 seconds. If we will take a look at the P19 at this graph, there is all this request which is down here. They serve within 60 milliseconds. But everything what is the above serve with either 100% of millisecond, not 100% millisecond, not percent, 100 millisecond or 150. If we will take a look at the P19, for example, and we say it's like 3 seconds, it means just 1% of the request took 3 seconds or more. The rest of 99% of your traffic took less than 3 seconds.
Okay.
I will.
Yes. Yeah.
I will tell you one practical example. For example, you are selling your services to some customer, and the customer asks what is the SLO of your system. That means for how much for P90, that is 99% of the requests are served within this much time. And you say that my SLO of my system is 1 millisecond. That means you are saying that 99% of the requests will ensure are completed within 1 milliseconds. When you're selling a service to a customer, you usually have SLA, the agreement, and the moment you don't meet them, that means if 99% of the requests are not meeting within 1 milliseconds, you are obligated to pay some penalty, or they may pull back their purchase, etc. So that's why this P90 the percentiles are important.
Okay, so for example, if in this graph, right, let's say the SLA says that my request should serve under 30 seconds. So are you saying that if I look at this graph, it means that I have to make improvements because it's only hardly 50% of requests are able to meet that condition, and so we want to still do improvements or optimizations to meet that SLA, isn't it?
That's
Yes.
correct. So not only for while selling, even in your system, you usually keep the dashboard of all the metrics. So your system keeps sending the information about how much time to process this request, and the dashboard will calculate this percentiles and keep showing the numbers. The moment it falls below certain threshold, you can get paged, you can get called, the developer can get called, they need to jump in and fix the problem, ongoing problem. If it is a long going performance issue, not a blocker, then you need to, in the offline, you need to work on that and improve that. So it's not just about selling, you need to have a dashboard set up with showing these metrics all the time, and you need to keep monitoring them. The moment it's going falling down, you need to jump in and fix it.
Right. Okay. Thank you.
So and there is we're calling them tail latency. It's usually referred to the slowest response time in the system. Typically measure the high percentage response, such as P95, 99, or even more. So it's captured the worst case performance experience by a smallest percent of the users or a request, even when the average latency looks fine. What can potentially cause the high tail latency? Is if you're working on a Java project, so it apparently could be garbage collection cause it. It could be caused by low attention or thread starvation. It could be caused by network jitter or package loss. Cold caches, cold start functions, noisy neighbor in the cloud environment, long garbage collector or memory pressure in any microservices dependencies. So this is just what the call start function. So for example, when you just when you just start not like service, it's probably better to explain with the Lambda. So for example, when you're using AWS Lambda, it has call start. When you just provision your Lambda, and it's just taking the request. So you're spending time on the provisioning of the your Lambda in order to process your request. And this is cold start, we call, when you need to wait while your, for example, function will be just spin it up. Or, for example, what could be cold start? For example, you're serving some request and you need configuration in order to understand how your request should be served. For example, this is like in order to know this configuration, you need to download them from something, from a S3 bucket, for example, or from some place. Usually it's not present on the server machine because it's first request, which is you need to serve, but you need to understand how to serve it. It also could be cold start because you need to download this configuration first. Once you download, you will save them in the on your local machine. And the second request will be served already quicker than the first one. The same about cold cache. First request, it's usually cache miss. Once you fill out your cache with the data, so you will second your request will be served more quicker. So where does 3 seconds come from? Is it something I measure on my existing service and then can promise to the client, and I'm supposed to calculate the time before building the service and then make sure it works accordingly? When you build system, I can speak from my experience. So basically, when you are just about to launch your system, you build your system, right? You know how it is act. You run multiple tests. You run some stress tests. You run some load tests. You do understand how your system is actually working, and from this point, you have your SLA. Which is you promise your customers that your service is going to act in these ranges. Shailesh, do you want to add something to this question?
Yeah, you're right. So, when you are developing a system from the scratch and selling it, you already measure the performance. So you know what is the benchmarks of your system. Then that's when you go and tell the customer, this is the performance of my system, and the seller can decide to buy it or not based on the what are your competitors are offering. And once you sell them, then you need to keep those thresholds. So you always need to work on your system to ensure those are the system is following those numbers. You can give the better performance but not the lower than what you promised to the customer. So when you are developing a system, you probably develop a system which says you are saying that 3 milliseconds is the P99, but your competitor is already offering 1 milliseconds. In that case, that's you probably need to redesign or may need to improve in your system before going and selling it. You if you are the only one selling, it's a different thing. But if you have already have competitors already doing better, then you'll have a tight competition there.
Yeah, so low contention, I believe it's understandable. So when you're working in a concurrent environment, so there is low contention for the lock, right? When you have a shared resource and you have 100 threads which will compete for this shared resource, and there is we're calling it low contention. It's at overhead how you quickly process something. And if it's designed wrongly, I mean, your concurrent system, so it's quite often where you're adding overhead for your latency, because it comes with context switching, it comes with log contentions. So it's quite a deep topic and low level as well. Network jitter in brief. So basically, when you're sending some packages over the internet, they are also coming with different packages, and it is like with the request. There is no guarantee that your packages will come within the same range of time. Some packages can come with delay, and it will also add some network delay. But it is also a very advanced topic. You don't really need to cover it during system design interview. Cold cache, cold start, it's nice to understand. Yeah, low contention, garbage collection, if it's some like Java/system design interview, also nice to understand. Yeah, noisy neighbor, it's more to cloud infrastructure. It's also, I don't believe that it will pop up during the system design. So moving on, because we
Yeah, if you have time at the end, I can give you examples for them, but let's first focus on this because those are specific concepts which needs deep dive. But
yeah.
If you have time at the end, we'll do that.
Yeah, okay. So throughput, we cover latency. As a part of performance, there is another terminology, which is throughput. It is rate at which something is processed. It could be requests per second, it could be database queries per minute, or network package per hour. So higher the throughput, better the performance. How to increase this throughput? So we need to decrease latency. The less latency means you spend less time on processing some requests, and means you can process more requests, right? So this is quite natural. You need to decrease latency in order to improve your throughput. Another option is to scale system vertically or horizontally, as we discussed. So to scale, like examples, to scale writes, we are doing sharding. This is some system design concepts which is will deep dive and which we're covering from one meetup to another one. To scale reads, we need to add some replicas. Regarding the, for example, when you're uploading some big files on Google Drive, or you're uploading big files on the YouTube, usually we're dividing these big files into chunks and processing them in parallel in order to increase throughput. Example is a message, just quick example. So in order to scale the processing of the message, you usually adding some more consumers, but because of consumers can't read multiple consumers, not in every messaging system can read from the same message queue, so you need to partition your queue as well. This is kind of examples. So this is all about the performance. It's throughput and latency. Moving on to durability. Durability, what does it mean? It's once data is successfully submitted to the system, it's not lost. How system achieve durability? Durability is achieved by creating and maintaining multiple copies of data. One is instrument is backup and another one replication. Regarding the backup, I don't really want to go quite deep about it. There is different strategy. I will better ask Shaileja. She will probably add more on durability. So a replication not only increase durability, it's also increasing availability and also increasing the read throughput as we cover. So, Shaileja, do you want something to add on the durability here?
Actually, durability requires further explanation. It's a very important topic, and it's very difficult to understand. I want to use my pad to show them few examples. Is it okay if I present?
Yeah, absolutely.
Okay. Okay, so durability means once you said to the client that I have taken your request, your data is stored. Once you say that, you have to keep the promise. That's the durability. But really, in systems may not be doing that immediately in the backend because they're probably doing some optimizations. For example, if you take a simple, sorry, take a simple database. I'm taking simple database, but durability can happen in various stages. So just take simple example. Let's say you're trying to write user one is having, let's say, some account details, you change the password, for example. Let's assume, or change the email ID to be simple, let's say. When you say that, user says it changes the email ID, the request comes to the database. Database takes the request first, it keeps in the memory, saying that user has changed the email ID, and it to actual disk. Probably the database has not written to the actual disk because it does so many optimizations. It maintains the in-memory buffers, and it doesn't flush them to the disk immediately. It does flush them to the disk periodically. For example, it is flushing to the disk every 10 milliseconds, let's assume. Because disk flush is a very expensive operation. Each disk write takes a lot of time, and we don't want the user to keep waiting until the disk flush is happening. Not only that, in case of the SSD drives, every time you write, you are really burning the actual flash drive in the back end. So we want to reduce the number of writes over the time in the lifespan of the SSD. So various reasons, when the database takes the request, it keeps it in memory and says that, okay, go ahead, I'm done. I made your changes. Now, as a user, what you think? Okay, my email ID has changed. But let's assume before 10, this change has happened at 1 millisecond. Before 10 milliseconds, let's assume the data center or the machine has lost the power. So entire machine is crash. When the crash happened, this change was in memory. It was in the RAM main memory, not went to the disk. Now, when the database restarts and comes up, the memory is empty. It doesn't have this change. Now, when user goes and checks, the email ID is the stale one. The disk is having the older one. So the change is not happening there. But when you once you committed to the user saying that I have made a change, and you have to keep the promise, that is the durability. And durability means no matter whatever you're doing in your system backend doesn't matter. Once you said okay, I'm done, it has to be persistent. For that reason, we do implement various mechanisms in the backend, something like write ahead log. For write ahead log is a small log records of the changes. Instead of writing entire block, usually block is a 4K size, but your change probably just few bytes. Instead of writing entire change to the disk, you're probably just keeping a something like assume ledger of the changes. So you're simply writing that U1 has changed the email ID. When the system is database has restarted after the crash, it will go and look at the logs. It will apply those changes to the disk, so it will bring back the change. Initially, when it committed to the user, it was not applied to the database yet, and the system crashed. When it is coming back, it is looking into the ledger of the changes and applying them and recovering the data. So this is a simple version of the durability. Once you said okay to the user, no matter whatever is happening in your system, you have to persist it. You have to recover it somehow. That's a durability. And this is simply at the database side. Whereas in case of the larger systems, scalable systems, especially when you are having a replication, for example, you are having a 3 replicas. You made some change here, even though let's assume it was written to the disk as well. It got written to the disk. And because we are having the replicas, the same data should be replicated here. But let's assume to the client, you said, okay, your change has got written, and after even the replication takes a bit of time because this is over the network, the change takes time. Before the actual replication happened, let's assume this system completely died. It's not even possible to recover it. In that case, you're not having the change in your system. The replicas are also having the older data. So that's how the durability is important, and it is important at various stages. So it's very important you understand this concept thoroughly. In case if you don't understand this well, we can have another session specifically for that one, but it's very important you understand, because system the interviewer may ask you to test you what is your understanding of this kind of corner cases, how are you going to handle them. So they may ask you the questions. Yeah, I'm done, you can present.
I have one quick question. Is the write
Okay.
ahead log separate? Is it on a separate server from the database itself? Because
Various systems have different I did work on different systems, so it's different from different systems. Some enterprise level systems which are quite powerful and need to ensure them, they may keep this log, write ahead log, and nvram. NVRAM means it's a normal main memory, but it's battery powered. That means even after system dies for certain time, it keeps having the battery power, so it keeps the data. It doesn't die immediately when the system died. In between, within that time, it's not for a long time because it's battery operated, but within that time, your system should be able to read from there and apply changes to the replicas. There are other places where simple commodity machines running them, they do have this write log on a normal disk, simple disk. They do have a checkpointing of writing them to the disk periodically. This write frequency is higher than the normal disk block write frequency. So this gets maybe written to the disk every few nanoseconds, so on. So that way, this write ahead log is persisted to disk. Even in those cases, it's possible to lose the data. For example, you're writing data to every few 10 nanoseconds. Even then, it's possible to lose power within those timelines. So we can replicate write ahead logs as well to the other machines and keep the data other places. So there are very different strategies depending on the system where the write ahead log is stored.
so it looks like even the write ahead log is storing the data on a disk, right? So how is that write less expensive than the database side's disk write?
So let's assume you're having 100 requests per second going on in your system. For all those changes, this block that we are writing to write log is just append only. Keep appending them. Let's say request 1, request 2, request 3, so on. It keeps appending. The one thing is there is no disk arm movement. Disk arm always sits here, so it's very quick to append. So that is and that's one thing. Second thing is, because all the requests are going to the same block, it gets filled up quite faster compared to the normal disk. In case of normal disk block, the data block, We don't just write anything into a block. The block is structured such a way, for example, in case of a database, it's probably structured one such a way that a set of database records pertaining to a particular table T1 with the trailers having the checksum, etc. So it is having a certain format. There can be hundreds of many of such data blocks in memory. You can't keep flushing every one of them. But whereas the write ahead log is having the data from different tables, different users. So if you just append only any incoming request, it will be coming to this write ahead log. For example, this data block changes over the time of 1 minute, probably will get 10 changes. Whereas write ahead log, within few milliseconds, it gets filled up and it gets right into the disk faster, because it's not any particular user or particular request. So it doesn't have to wait for it to be filled. It gets any incoming request, we just keep appending them, and so it's faster.
Okay, thank you.
Yeah, it's very very scope to not very scope to database message system, also using write ahead log. It is a very internal one. But we will go deep on this topic if you lost now. And we will explain why it's quick. Yeah.
Name may change, because in case of databases we call it write ahead log. In case of the distributed systems, may call it different name, journaling, or the just a ledger. It could be any different name, but overall the concept is the same.
Yes, I mean, yes, why it's quickly, because you're just appending, and yes, the concept is the same and it's used. But yeah, when it comes, for example, during the system design interview, probably you should know this concept, like having log file where you are appending all these log records, where you can just after your system is crashed, you can restore from this log. This is one thing. But during the interview, you should know that you need also create backup of your system. How you're creating this backup of your system? How, for example, when there is some services go down, how when you bring them back, how he is going to catch up on the difference, how you're going to restore this kind of concepts, we will cover during the during probably system design interview, where we will take some examples and yeah, how it works. So it will be more clear later. Let's move to the consistency. So because it's quite I would say from
you need to present.
Sorry. Yeah. And also, I believe we didn't record this session, folks. I will record last consistency steps, but we didn't record them. Okay. So consistency. What is the consistency? Yeah.
Can you present only that particular window? It's creating infinite loop of the mirroring the page.
1 second. This one.
It works good.
Okay, consistency. This is another one non-functional requirement, which is quite broad and used in different terms, like as a part of ACID, as a part of CAP theory. Let's dive deep what is consistency means in terms of non-functional requirements. So where I will step back a little bit. In past, when we have a single active database, for example, as we discussed, we need to have backup storage for durability, and we need standby mode for fault tolerance. At this case, when client is writing something, he is writing in the one instance, and he is reading from the same instance. Means there is no copy of data happens, even though, yes, we have backups and we have standby mode, but everything is read and write from one instance, and and we use the same copy of data. When the consistency is came to the picture, when we have different instance of database, And we write in one database and we replicated them in different instances. And we read from different instances, means we can read different copy of this data. And in this case, there is could happen some issues. So basically, as we discussed, we can write some copy of data, but it's not yet replicated. And when you read from this instance, you will read the stale data. We're calling it inconsistency. Yeah, let's look at the consistency models. There is we have strong consistency and we have weak consistency. When we're speaking about strong consistency, we mean linearizability terminology. When we're speaking about weak consistency, we mean eventual consistency. I will provide more consistency model just later on. Just will explain what is the strongest consistency and weak consistency mean. So the strong consistency means that after update completes, all client when they read data get back their updated data. Typically, it's used for banking, e-commerce, booking system, or distributed log. Also, learnability is very slow because when we are having some replication, we need to wait while this replica will accept a new value and will report us back. There could be different issue. It could be fast, but it could be that some replica is went down and we're waiting endless response from this. This can slow down the response. This is one example. Also, as a part of nuance, but we will cover it deeper, the CAP theorem. Consistency in CAP theorem is actually means linearizability. What I mean
one correction, that's not correct. That statement is not correct. Consistency in the CAP theorem says, how are you going to have a CP over A? I will cover it in a separate session, but that particular statement is not correct.
I mean, here you're speaking about learnability. Once you go with eventually consistency, you can tolerate network.
So CAP theorem just says you should have strong consistency. It can be eventual consistency as well, but it just explains in case you are having a strong consistency, how availability or the partition tolerance is going to be impacted. So it doesn't say that you need to have this one over the other one. So that's a different session. I will cover it up.
No, what I mean in this, we need sacrifice consistency over availability if we tend to have strong consistency. But if we're speaking about eventually consistency, it's fine we don't need to sacrifice availability in this case because we already know that there is eventual consistency. Means any network partition failure is not affected us in this case. But if we're speaking about strong consistency versus availability, then yes, we need to make this trade-off. But when there is context eventually consistency versus availability, you don't need to take this trade-off, right? That's what I mean. Because you already promise eventual consistency.
Okay, let's discuss this in separate session. We'll go into that.
Yeah, when it comes to weak consistency, inconsistency video, inconsistency, so what does it mean? If there is no additional updates meant to the object, eventually all reads will return the latest written value object, but there could be some inconsistency window. Usually it's very small, it's a sub-second, and eventually consistency is much faster than learnability. And as I explained it, you don't need to sacrifice availability because you're already promising eventually consistency here. But let's speak about the problems which comes with the eventual consistency. One of the problems is disappearing comments. For example, you saw one comment, you send request or you refresh your mobile phone or Instagram, and comments is just disappear. Also, you put your own comments, and then you just refresh your page, and you see that your comments is actually disappeared, but you just posted it. This is kind of two problems, which is why it could happen. So there is clients which are sending first request. and he reads from this replica. And this replica has comments. But second request comes to another replica, and this replica do not have it. The second problem is the same. Another problem, out of order comments. So, for example, you are seeing some comments and you are reply to these comments. But after refreshing, you see your comments come first instead of the second. And there is lost the order of the comments. Why it could happen? When the first comment comes to the shared one, and the second one comments to come to the shared two, and replica shared delayed, for example, but another one succeeded quicker. So that's why it could happen. To solve this issue, we have another additional consistency model, which is monotonic read, read your writes, and consistency prefix read. From the perspective who is weaker, who is stronger, they equal one. And we will cover in deep this consistency model. For now, I just want to show what kind of consistency models we have. So, and on this note, basically, I'm finishing this two session on the terminologies. This is terminologies which we cover so far. This availability, scalability, performance, durability, and consistency. So, yeah, I'm finished. Any questions?
We are out of time. Do we want to continue or should we catch up in the next session?
No, I'm finished with my lecture for today.
Yeah, so
I do have a question if I can. I'm quite new to system design, I must say, but I'm trying to arrange all this information somehow between what's been taught last week and this week. How do we do this? Just go through those information that you presented last week and this week and put them and try and digest every single concept, or what's your advice? How we should go with all this information?
So, in my opinion, we have a slightly different opinion with Shalaja on this one. In my opinion, it's nice to understand from the system requirements. What does it mean, system requirements? What is the functional and non-functional requirements? Once you understand what does it mean, there is non-functional requirements, which include these terminologies during the system design interview, which is availability, scalability, performance, durability, and consistency. All of them, these requirements can meet by different system design concepts. Once you know what is the availability terminologies means, I would go and learn all system design concepts which will solve availability non-required. Then I will move to scalability, then to performance. Some of these system designs concepts which we will learn, they can solve different these non-functional requirements. It doesn't mean that, for example, replication can solve availability, can solve durability, and performance requirements. So, in my opinion, it's nice to understand these non-functional requirements which exist. It's not that many. This is 5. And there is 3 more, which is not very popular, but this 5 very popular. You need to know, you need to understand these terminologies. What does it mean? And then we will start to cover system design concepts, and we will cover what these system design concepts for what, to solve which non-functional requirements.
So in the upcoming meetings, we're going to go one by one through this system requirements and deep dive into every single concept. That's the plan.
We did it. We started it last time. If have you been on the first meetup?
Yeah.
So I cover actually what the system requirements, right? I cover what is non-functional, what functional requirements. Then I cover availability. And today I cover these 4 terminologies. What scalability mean, what performances mean, and durability and consistency. We a little bit we mentioned so far system design concepts, which is probably confusing now people because it was very brief. We just mentioned the naming of system design concepts, but all these system design concepts, which is we mentioned today and on previous 2 sessions, we will cover in deep on our next meetups.
Okay. Thank you.
Yeah, welcome.
Lilia, it's Irene here. I've got a quick question. Thank you for the session, ladies. Just wondering, because the recording went, I was keen to go back over because some of the parts that you were discussing went really quickly for me. I recall you transcribing notes. Will you be making those available to us?
Yes, the first one I've already provided, right? The whiteboarding, and this one I will provide just after. The first.
I thought, separate to your whiteboard notes, which are great, I wondered if you had software running to transcribe the session notes. So as you spoke, it was recording what you were saying. Are you making those available?
We didn't make the recording, but what I can do, if you want, folks, I can make the recording offline and probably record them and just share.
So can you say that again, please?
I mean, for this session, we forgot to click recording.
Yeah. So you don't have any recording of the actual session at all?
Of this session, no.
So
But
no recording and no transcribe of what's been said. In that case, is there any chance you can leave the Google meeting up for an hour so I can go through the captions and look at the comments through the captions then?
yes.
That'd be possible.
Yeah.
Unfortunately, you can't copy them, but I can go through it quickly and take any notes,
Okay.
additional notes, if that was possible.
Sure.
Thank you. Thank you so much.
Okay, bye then.
Was there a recording last week, please? Because I didn't receive it.
Consistency was recorded.
It was last week.
The last one, consistency, was recorded. The last week was recorded as well.
Yeah, where can I get it? Because I didn't